Hello, my name is Nicholas Benjamin G. Abot, and today I will be discussing fractal design and technologies. I will be covering what fractals are, their history, how to make some to give a better understanding, and how we can apply them in the real world. First of all, let's define some terms so that we have some grounding, because this field can sometimes get a bit dense. Now, one specific definition of a fractal is that its Hausdorff dimension is higher than its topological dimension, and it is a shape. Now let's define those two terms. Firstly, the topological dimension is whether or not a shape is point-like, line-like, plane-like, or so and so. For example, this shape is like a line, while this shape is like a plane. So this would have a topological dimension of 1, this a dimension of 2. The Hausdorff dimension, meanwhile, is a measure of roughness, and it's allowed to be a fractional dimension. As such, these shapes are examples of fractals, because this is line-like, as are all of these, but their fractal dimensions are higher. Another term we'll need to know is self-similarity. Self-similarity is the property of a shape of having, when zoomed in, multiple copies of itself within itself. So for example, this fractal, called the Sierpinski triangle, has 3 copies of itself. Another version of self-similarity, called quasi-self-similarity, applies when, zooming in, you get slightly distorted versions of the original shape. Other versions of self-similarity include simply having similar roughness at different scales. One of the first kinds of fractals is the theoretical fractal, which are usually mathematically exact and have exact self-similarity. Some examples include the Sierpinski triangle, the Koch curve, sometimes made into a Koch snowflake, the dragon curve, the Menger sponge, and the Mandelbrot set. Next are natural fractals, because importantly, fractals occur a lot in nature. These include rough coastlines, structures in plants, such as trees, structures in chemistry, such as deposition and snowflakes, and structures in anatomy, such as blood vessels and bronchi. Now, some properties that fractals have include self-similarity, as demonstrated by this GIF here on the Mandelbrot set, and also properties relating to infinity, such that in some measures they have infinite length or area, or have 0 length or area, depending on what's being measured. Also, there are strange properties when it comes to scales, as will be demonstrated now. Now, in normal shapes, the measure of the shape scales with the scale factor to the power of the dimension times the original shape. So this means that one-dimensional objects like lines scale to the first power, two-dimensional objects like squares and triangles scale to the second power, and three-dimensional objects like cubes scale to the third power. However, for some shapes, like fractals like the Koch curve or the Sierpinski triangle, scaling them up does not give a simple power, and instead give dimensions like 1.26 or 1.58. This is the general method for computing a Hausdorff dimension for self-similar shapes. Next, let's look at the history of fractals. Early concepts related to fractals began when Leibniz was studying fractional exponents and wondering about whether or not examples of geometries that relate to this exist. Now, examples of fractals in serious mathematics began with stuff like Weierstrass's function. First function that was discovered that was continuous and everywhere but differentiable nowhere. Then there's also the Cantor set, which has some strange properties as a set. However, due to their strange properties, most of these were branded as monsters, and not quite taken seriously by the mathematical community due to the weird properties they inherited from infinity. Then more intuitive fractals came about. These included the Sierpinski triangle and Koch snowflake, which have easier to understand geometric definitions, whereas previously the previous two fractals were only defined in set theory or calculus, and sometimes were not given a graphic representation at all, and also in the realm of algebra and complex numbers formed the Fateau and Julia sets. Then, Benoit Mandelbrot came along, and thanks to his job at IBM allowing him to better visualize these shapes, he brought them under one umbrella that he called fractal, based on a Latin word that means broken because of how jagged they appear. This gave way to modern ability to apply them, which includes train generation and using them for electronic devices such as antenna. Now, let's show a few ways to construct fractals so as to give a better idea of how they work. First are iterated function systems. The basic idea of this is to take a whole and replace it with a few smaller copies of itself, which I will demonstrate now. Iteration function systems are made out of a base, which is repeatedly replaced with a motif made of possibly a few copies of the base, repeated infinitely to produce a fractal. Next are strange attractors. Strange attractors are made by defining a function for a velocity of a point in a given space, and then finding where points end up in that space, which is called a strange attractor. Examples include the Lorentz attractor and the Rosler attractor. Next are L systems. L systems are sets of symbols that start with a basis called an axiom and a set of rules to replace that axiom, with each symbol representing something. You repeatedly replace to infinity, but if you cut off at a finite point, you get results like this Koch curve. Some of the ways they can be used include producing fractal trees, and also many other fractals, as they can also be used to generate iterated function systems, and also other ways to generate fractals, such as this curve-based version of the Sierpinski triangle. Next are escape time fractals. These include the Mandelbrot set and the Julia and Fateau sets, and also the Newton fractals, which are based on methods of finding roots. Escape time fractals are made when one iterates a function on the complex plane and then checks for a certain property, such as if the point, once iterated, goes to infinity or stays within a certain radius of the origin. Lastly, we have random fractals, which, along with some of the previously mentioned methods, include elements that create randomness, so that it's not the same every time. These include random walks, whose shapes after a long period of time can form fractals, and also simulations of chemical deposition, such as diffusion limited aggregation. Lastly, we'll look at applications of how we're able to use them. One application of fractals is the antenna. Due to the properties of fractals, they make for a great way to cover a lot of surface area using a small amount of material. And due to self-similarity, they're able to cover a large range of frequencies without needing extra equipment. This property also has some implications for some properties of the electromagnetic field, so they've contributed to our understanding of that as well. Another application of fractals is fractal analysis, where one takes a dataset or a network and compute its fractal dimension in a certain sense of geometry, and uses that either as a measurement to determine if something has changed, or to determine the complexity of a network. This can be used to identify problems in biology, or to identify complexity in, for example, social networks. The last application of fractals I'll discuss is procedural generation, where using random fractals, one can break down simple shapes into complicated terrain, or using iterated function systems, simulate and generate nice and simple to compute plant designs. In conclusion, fractals are a beautiful and very important aspect of mathematics, as it is one aspect of it that allows us to incredibly accurately model the real world and allows us to understand it much better. Anyways, thank you for watching.